Okay, given A plus B goes to AB, if one of the components, A or B, is in excess and the other one is then in a smaller quantity than 1 to 1, then the smaller mole number will be the limiting reagent. Now, let's say this is A, the water is A, and this is food dye, and that's going to be B. So if I put a small amount of B in there, what's going to happen? It's going to consume all of the B, and you're going to have a lot of water left over in the reaction process, and it will distribute itself through, but you'll only have AB in the end of this reaction. Okay, and the water is A, but B will now not be present, even though it's showing blue, but now the color AB is blue. So the one that's in smaller amount is the limiting reagent. Okay, how do we determine that, which one of the components in a chemical reaction is the limiting reagent? Okay, let's see, you're given 10 grams of hydrogen gas and 10 grams of oxygen, O2 gas. How much H2O will form? And so we have to determine what the limiting reagent is from the chemical equation. Well, hydrogen plus oxygen produces H2O, and we'll make that liquid. And this balances in the following way. Now, we've given 10 grams of each one. How many grams will be produced? Now, I talked to you yesterday, regardless of what the data is, convert it to moles. And then in this case, we divide by formula weight in each case. So divide by formula weight, we'll divide by 2 grams per mole, and 10 divided by 32 grams per mole. And so that gives you 5 moles here, and 10 over 32 0.31 mole. Now, which of those is the limiting reagent in here? Well, you can throw that out, but that's not the way to determine what your limiting reagent is. There's a simple trick, and there's logic to it. Once you convert your data, grams or whatever it is, to moles, divide the mole number by the respective coefficients. The smaller number in that case is the limiting reagent. So the coefficient is 2 in this case and 1 in this case, which gives a 0.31 number, and this one of course gives 2.5 number. The smaller number is your limiting reagent. Is the limiting reactant. However, if when you divide all this out, you have to come back up here to the mole quantities and then solve the problem based upon the limiting reaction. because that's what governs the output of the reaction itself, not the excess over here. Now this isn't exaggerated in terms of the amount, so you can see them clearly. So in this problem, it's a 1 to 2. So the amount of water would be based on the coefficient of oxygen to water. And if we've given 0.31, we simply double it, and the yield would be 0.62 mole. And if we need grams times 18 grams per mole, because the formula weight, whatever that gives us, I think 11.25 grams. Because the limiting reagent governs the output of the reaction. Okay, you're given this reaction. It's called a rebreather reaction because it's using potassium superoxide is what that's called. Reacting with water to produce potassium hydroxide and generates oxygen out of this reaction. Now, what they're asking is how much oxygen, how many moles of oxygen will be produced given 0.25 mole of potassium superoxide and 2 moles of water to produce the oxygen. Now, the issue is the amount of oxygen is going to be based upon the limiting reagent. So you need to determine which one of these two is the limiting reagent. So the trick I gave you, the rule I gave you, is divide by the respective coefficients. The smaller number is the limiting reagent, and then you work your problem around the moles of limiting reagent. But you have to come back up here and the given to work the moles. So we want to divide this 0.25 by 4 and 0.15 by 2. And that gives you 0.0625 for the potassium superoxide and 0.075 for the water. Since this is the smaller of the two numbers, that's the limiting reactant. So you come back up here and work the problem based on 0.25 mole. This will remain in excess. That is, you will have extra water left over once the reaction stops. So we look at the 0.25 going to X. Over here, X moles against 4 going to 3. Well, it's going to be a smaller numbers. Here, by how much? By 3/4 of what's given. So you have 4 going to 3. 0.25 needs to go to a smaller number. Well, you take the coefficients of the limiting reagent and the target compound and set a ratio that will make 0.25 smaller. You don't want to use 4 over 3 because that will make 0.25 larger. So you take 3/4. So this would be 3 over 4 times 0.25 mole of O2 is yield. And I have 0.1875 mole O2 gas. So the issue is reaction and data given. How do you choose the limiting reagent? You divide by the respective coefficients, which we did here. That's a trick. Actually, what you're doing, if you took this, and this is the given right here, convert that to 1. Divide through by 4 on everything. And once you get that to 1, that would be the limiting reagent, or whatever you convert. But this is the easiest way to deal with it. The smaller number after you divide by the respective coefficients. Then work back at, like I told you, go back up to the 0.25 or whatever's given and work the problem from there. Nasty looking critter. Okay, yeah, that's the given. Titanium oxide reacts with carbon, chlorine gas, produce titanium chloride, CO2, and carbon monoxide. It wants to know how many grams of titanium tetrachloride can be produced. Titanium, for general FYI trivia, is used as the primary material in the construction of the SR-71. Anybody know what an SR-71 is? Yeah. Fastest jet on the planet. Okay, it's kind of a CIA, but it's been retired, I think, and pretty much. And but it's got an interesting history. Yes, you look up the SR-71 spy plane or something like that. But anyway, it's built out of titanium because it goes so fast. Anything else that'd be made would melt. And so I think it goes Mach 3 or something, if I remember roughly. And anyway, to get the limiting reagent out of the givens, how do you do it? Well, the rule is what? What's step 1 after you write your balance equation? Convert to what? Moles. Okay. How do we do that? Divide by formula weights. Well, I put the formula weights up here, and so you can shorten your effort. And I figure you know how to determine those anyway. So what we want to do is divide by 80 and 12 and 70 to get the moles of each component in the reaction. And so we're looking to start with moles. How many moles are generated, and that number will be based upon the limiting reagent that we determine over here. So to determine the limiting reagent, what do? Divide by what? The respective coefficients, yes. So we want to come in here and divide by 3, then 0.473 divided by 4, and 0.097 divided by 6, and this will give us 0.05. Okay, well, this looks like the limiting reagent right here. And when we divide by the respective coefficients, this one is, again, the smallest. So we come back up here and work the problem from 0.097 mole. So we're talking about titanium chloride in the yield side. So we see it's a 6-3. So it's a smaller number by half. And so the moles of titanium tetrachloride, if is a 6-3 in the equation, it would be half of this number, or 3/6. Of course, that would give you a half. 3 out of 6 will make a smaller number. Now, titanium is 48. So we go 188. So we want to multiply by 188 grams per mole for the titanium tetrachloride. And I have 9.12 grams. So you want to review this for sure, because it's going to be used more times than any of the other exact values for stoichiometry. One, balance the equation, obviously, and then apply, convert to moles, and then divide by respective coefficients. Smaller number is the limiting reagent. Work the problem in moles given. And once you determine that, if depending on what they're asking you for, if they're asking for grams, you need to multiply formula weight of the target compound by the moles produced. Now that's called a theoretical yield, which introduces the next topic. So when we're talking about 9.12 grams yield, this is essentially a theoretical yield. The theoretical yield is the value calculated from the stoichiometry of the equation. Actual yield is what really happens. So that's where we are now. Theoretical yield is the yield from equation stoichiometry. The probability of getting a theoretical yield out of a reaction is very limited, and there are a number of kinetic factors that come into play, but no reaction produces 100% per the stoichiometry of the reaction. The actual yield, or sometimes called the lab yield, is the true amount produced. True being actual, real, reality, whatever. Percent yield is the actual yield divided by the theoretical yield times 100%. Very straightforward calculation, part over total. There it is. Let's calculate the theoretical yield, percent yield, where the actual yield is 1.86 grams. So one notation is the theoretical yield is going to be greater than the actual yield. It's always greater than the actual yield, and then we're looking to do the percent, which is the actual over theoretical times 100. So that's the objective here. Now, the approach is convert to moles and divide by respective coefficients. Well, everything's 1-to-1 reaction ratio, so divide, whatever the smaller number of moles in the reactant side, that's going to be the limiting reagent, because it's a 1-to-1 and it's going to be 1-to-1 here. So we want to simply divide this one by 138 and this one by 102 to get the moles of reactants. And 0.015. And 4/102 is 0.039. Well, since the C7H6O3 is the smaller mole value, this one, of course, is the limiting reagent, or reactant. So our problem is the moles of C9H8O4, whatever it is dependent on this. So since it's a 1-to-1 reaction ratio, then you can conclude quickly that the moles of C9H8O4 theoretically is going to be 0.015. In converting to grams, we multiply by 180. This is salicylic acid, and this is acetic anhydride, and this is acetylsalicylic acid. Anybody know what acetylsalicylic acid is? It's aspirin. So this is just an equation for synthesis of aspirin. At any rate, so we're talking about 0.015 mole of C7H6O3 will produce 0.015 mole of aspirin, C9H8O4. Because the rest of it is irrelevant, because this is acetic anhydride and it's going to wind up as an excess. So we don't even put that into the calculation. It's always in pairs. Okay? All right, so the idea is to get this to grams. Well, I give you the formula weight here, so what do? Multiply by 180 grams per mole. And we have 2.7 grams yield, theoretical yield, I should say. There. So the percent yield now is the actual over theoretical times 100%. So that is 1.86 given, divided, make it look like an 86, 1.86 divided by 2.70 grams. Grams will, of course, drop out, times 100%, and 68, 69% yield based on the data given. Any questions? So convert to moles, divide by respective coefficients, limiting reagents defined, then you work the problem based on given moles. And once you get the given moles times formula weight, if that's what it's asking for, and then calculate your percent yield based on actual over theoretical times 100. Pretty straight, okay? Definition of a solution. We've mentioned in the beginning chapters is a homogeneous mixture